Well, welcome everyone. This is our second faculty seminar. It's being sponsored by Carnegie Mellon's University Transportation Center. Some of you folks may not know we have a University Transportation Center, but we do. It was actually triggered by, this is kind of a roundabout explanation, but it was triggered by a special effort that started in late 2008 through the inspiration of a local Pittsburgh philanthropist, Henry Hillman, who helped to seed some efforts to take advantage of transportation technology work going on at Carnegie Mellon. That was put into a framework called Traffic 21 Initiative, which basically scanned through the university and identified a lot of different transportation research going on, one of which is going to be discussed by our speaker. But that allowed CMU to think that it could compete on a national basis when, in 2011, the United States Department of Transportation revamped and recompeted something called their University Transportation Center program. Needless to say, Carnegie Mellon was successful, and in January of 2012, CMU has now one of the 22 national university transportation centers across the United States. Our CMU University Program, or Transportation Center Program, is a partnership of CMU and the University of Pennsylvania. And Steve is one of the folks involved in the program. Let me just say that you're in for a real treat today hearing about Steve's work. Steve is a professor as part of the Robotics Institute, where he heads up the Intelligent Coordination and Logistics Laboratory. Steve's research focuses on next-generation technologies for planning, scheduling, coordination, and optimization. And a real sweet spot of our university's Transportation Center program is taking research that has been developed and deploying it. And this is a great example of one of the deployments. Steve's involved in a number of projects in the adaptive signal control. He's doing things related to disaster response, automated manufacturing, and also another transportation project that is going to be coming up here pretty soon, which is special dynamic scheduling of paratransit systems. I think you may be familiar here in Allegheny County. There's something called the Access Paratransit System. Steve is working with that group and looking at ways to make that scheduling of that service more efficient and effective. And with that, let me just have you join me in welcoming Steve. Steve has got his undergraduate at Westminster College and his master's and PhD at Pitt in computer sciences. Please welcome Steve Smith.
Thank you. Well, thanks, Al. I hope I have enough time to give the talk here after that introduction, but it was great. I'm going to talk today about some work that we've been doing in my lab the past probably 4 years now. I can't take credit for the title of this talk, but I like it, being from the Robotics Institute. But it really centers around some new technology that we've developed in the area of real-time adaptive traffic signal control. My talk will, I'll kind of go, first I'll talk a little bit about traffic congestion and signal control, just to kind of give a very brief background on what we're talking about here. I'll spend some time then talking about the system that we've developed and the approach that we've developed in some detail. Then I'll turn attention to a deployment that we've been carrying out over the last couple years in East Liberty, a few miles from here, and a pilot test. And then I'll talk and the results that we've gotten there. We've been very successful in that deployment. And then I'll finish up with some work about our current work in research directions. So, there it is. Can you hear me all right? Okay, great. So the problem that we're really focused on is traffic congestion. As the slide indicates here, traffic congestion is a waster of time. It increases fuel consumption. It decreases air quality. I've put a couple statistics here on the slide. They're taken from the 2012 annual mobility report, which indicates or sort of estimates, concludes that the annual per capita cost of congestion to commuters here in Pittsburgh is about $826. This is measured in terms of lost time and added fuel costs. Nationwide, if the report looks at all major urban areas, and they estimate on a national level we're spending or we're wasting or it's costing us over $101 billion in congestion costs. So another study indicates that in urban areas in particular, we spend about 40% of our time on surface streets idling. So there's lots of, it's a problem, it's a great problem to work on because everybody can relate to it. And it's a growing problem in the US. Well, if I want to think about reducing traffic congestion, there are a couple kind of approaches. The historical approach has been to build more capacity. So if I have congestion, build my way out of it, add more lanes, build new roads. Unfortunately, in urban environments in particular, that's typically not a viable solution. Pittsburgh, for example, has tremendous geographic constraints for anybody who commutes through the tunnels. And so, you know, building out is not really an option here. And it's certainly one we're not going to think about further. Another kind of approach, meaningful approach to lowering traffic congestion is to start to think smarter about mass transit and getting vehicles off the road and sort of exploiting other kinds of modes of transportation. That is a very viable and laudable goal, and I'm not going to talk about that, but there's lots of good work going on in that area, and it's certainly an approach that should always be taken seriously. The third way I could think about reducing traffic congestion is to increase traffic flow, or to improve traffic flows, and that's really going to be the focus of this talk. You know, in the hypothesis that drives our work is that smarter traffic signals can help. You know, it's generally recognized that the biggest bang for the buck that you can get in improving congestion on surface streets is through better traffic signal control. And while they're not in wide use yet, adaptive traffic signal control systems, which I'll be focusing on today, are generally believed to hold the most promise for improvement. So before talking about adaptive, let's just kind of get a very basic sense of what we're after here. Traffic signals are driven by signal timing plans. And here's kind of a very basic idea of how they work. So I've got an intersection in the top left up there, east, west, north, and south. And typically, traffic signal plans are built by, first of all, looking at different movements that can move through the intersection and grouping movements into phases. Phases would be movements that are mutually compatible, that can move at the same time. So you can see I've labeled some of the moves there. So 2-6, for example, is an east-west flow. That can operate simultaneously, and so that's encapsulated as a movement phase. And then if a signal timing plan is then just a sequence of movement phases. So the determination of a signal timing plan is really to establish a duration for each phase, and then what sequence, typically in conventional systems, the sequence repeats. All right, so you can see there in the example I have on the slide, we move through 4 phases, and then that cycle repeats. Yeah, that's sort of a classic example. So the signal timing plan problem then, or the problem of generating a plan, is really to decide how much green time to give to each phase and in what order. So if I look then at conventional signal systems, really the distinguishing characteristic of that is that conventional signal systems use pre-programmed timing plans. So the plans that are built in advance, programmed into the hardware controller that's driving the light, and then they sort of operate on that basis. So they may be the result of some kind of offline optimization. You sort of look at the expected flows, do some kind of offline optimization, and then take the results of that, program it into the controller. And so sometimes they involve what's referred to as simple actuation. If you've ever pulled up to an intersection and driven over a magnetic plate, a loop that sometimes sometimes if you're lucky, you'll turn green and give you, feed you. That's the idea of a very simple example of actuation. The light will detect the presence of a car at the intersection, waiting, and then move on. So conventional systems take advantage of that kind of idea as well. Adaptive signal systems, on the other hand, really sense current traffic flows in real time and dynamically adjust the timing plans continuously. So, based on the traffic patterns it sees in front of it, adjustments are made. So that's the class of system that we're focused on. Our work has been focused on, and that's what we're talking about. Take a look at adaptive signal control systems that are out there in the world today. Adaptive signal control has been studied for, has been the subject of design for many years, and there are several systems that have been created and are out there. The most success has been gained by centralized systems that will take whatever detection is happening at the intersection, whatever view of oncoming traffic is coming, pull that back to a central location, do some amount of computation, and then push out changes to the timing plans that are driving the actual intersections. Given, as you kind of think about that process, often that can be very successful, but it's often can be limiting with respect to reaction in real time. So, typically or quite often, these centralized systems sort of operate on a time scale of adjusting the lights, sort of integrating results that are from traffic patterns, maybe combining that with historical information about the flows, and then making adjustments on the order of minutes. Every 5 minutes, every 10 minutes, et cetera, make some kind of a change. So the limitation it can be, the changes on that kind of a scale are not going to really allow me to respond to quickly to events like traffic accidents or I don't know, garage emptying at the end of an event, things of that nature, a little difficult. Other approaches, what I've called online intersection planning approaches, have really looked at this real-time problem of sort of how can I respond to events as they're actually happening in what we really think of as real time. These kind of approaches extend very naturally to control of networks using decentralized kind of ideas. However, they have tended to suffer from just the computational requirements of computing optimized timing plans in a time that can keep pace with execution. So that's one sort of obstacle that the techniques that we're working with or that we've developed overcomes, and that, in a sense, it will allow us to take this kind of approach to the problem. One other kind of class of systems, if I can make certain assumptions about what kind of flows are going to be in my traffic network, and in particular, if I can assume that there's a single dominant flow, say I'm in an arterial situation, there's a main road, and all I really need to do is kind of manage traffic on the side streets, then I can take advantage of that structure of the problem and sometimes do very, very well by using a shared global plan to control the main artery and then operate locally to manage the side streets. And in fact, there are a couple existing systems take advantage of this kind of an idea and can do very well in arterial settings. In fact, you see most of the success with current adaptive signal systems in arterial kind of settings. So one distinguishing aspect of the focus that we're really aimed at urban road networks, networks that have more of a grid pattern, and there's more than one. There are multiple, typically competing dominant flows, and those flows change over time. So it's not possible to sort of identify one single flow, and you need the system to discover that. So for the last, this is just a slide that it's been sort of using for quite a while now. About 3 or 4 years ago, we started looking at this problem of real-time control of urban road networks, sort of the missing link in current technology, or a missing link. So the goal of our work has really been real-time optimization of traffic flows for urban or grid road networks, characterized by the fact that you have multiple competing flows. So you have to really continually identify the major flows and go from there. We take, I'm going to say more about this, but very broadly, we take a decentralized approach. Our approach is totally decentralized. What I mean by that, and you'll see as we go along, each intersection will be responsible for building its timing plan and controlling its local flows. And then, so that gives us real close, we're actually computing right at the intersection, so we have the maximum opportunity to take advantage of real-time event, or to respond to real-time events. But we also can get coordinated action by just communicating information. So we communicate planned outflows to our neighbors, and then those neighbors, which are doing the same thing, can take that information into account. And that's what allows us to get sort of what are referred to as green corridors, as you're sort of driving, and the greens light up for you. Just a kind of a very brief project history. We spent a couple of years, starting in 2010, really developing the core approach, the core algorithms, improving them out in simulation. We used a model of the downtown Pittsburgh network, the 32 intersections down at the triangle, and we got very good results in simulation in showing the potential benefit of the approach. That led us to look for an opportunity to try it out for real, or try it in practice, and we found that in the last year and a half, 2011, 2012, we've been developing a pilot implementation of the approach and deploying it in East Liberty. It's been running there since last June, and our current focus is really expanding the pilot test site in various ways. So let me just kind of give you a little sense of the technical detail, the principles underlying the approach, and then we'll move on to the deployment. So the name of the system that we've built, we refer to as SURTRAC, Scalable Urban Traffic Control. We'll see how what that topic means as we go along. I have to somehow, there we go. So here's the basic concept of operation. There's detection at each intersection. What happened to my, what happened to my, there it is. All right, so the system is in our case, we've been using cameras, but the system is watching ongoing traffic flows. Those are extracted, so we extract the current traffic patterns from the sensor data streams. We're using cameras. You could use a number of other kind of detectors. Then our intersection scheduler will compute a phase schedule, compute a timing plan that optimizes the flow. It essentially moves the traffic that it sees in front of it through the intersection in a way that minimizes the cumulative delay. That's the objective that we're currently using. Then, after it builds a schedule, it then sends commands to the actual hardware controller that's driving the signal, telling it whether to stay in the same phase or move on to another phase. It also communicates the outputs, the outflows it expects from its plan to its neighboring intersections, which, as I said before, are doing the same thing, operating asynchronously, but as they build a schedule, now they have information about not only what that intersection is seeing right in front of it with its detectors, but it also has information about what's coming down the pike, so it's got a longer horizon to plan against. And then that whole process repeats every couple seconds. So it's a very real-time system, and there's the opportunity to adjust the timing plan really on a second-by-second basis. So there are a couple key technical ideas that underlie this approach. One key is the approach that we take to intersection control. What we've really been able to exploit is a novel formulation of that intersection control problem as a single machine scheduling problem. So what we use an aggregate representation. I'll explain. I'll give you an idea of what I mean there, of traffic flows, essentially as sequences of queues and platoons, and those really are what identify our input jobs from a machine scheduling point of view. And then we use the schedule to decide whether to extend or switch phases. So that's one key idea is that. And then with respect to coordination between intersections, we communicate schedules to downstream neighbors to give visibility of future input jobs. This idea, if you think about it, is a very simple idea, but it'll work perfect. It'll coordinate perfectly if intersections execute their plans exactly as they've planned. Of course, that doesn't happen all the time, and so we get situations where the plans get out of whack. So our approach here is to layer on top of this basic communication protocol some mechanisms for coping with specific kinds of miscoordinated situations. And that's really to account for the fact that the schedules might change. I'll say a little bit more about that in a few minutes. So first, let's look at the sort of model of how we model the problem, which is what allows us to get the computational efficiency. Here, if you think of a flow, this is kind of the information that assume I'm getting from the detectors. So my intersection's on the left corner here, and I've got a stream of vehicles approaching the intersection. Some are already in queue, waiting for now I'm obviously at a red light right now. So what we do is take that base level optimization and just do a simple clustering. So on one hand, we do what we call threshold-based clustering, which essentially just puts together vehicles that are in close proximity to one another into larger entities, which we'll sometimes refer to as platoons. So you can see there that given the proximity, we've got two of the vehicles that were floating really didn't get combined with anyone, so they just become their own cluster, and then the others, A second form of clustering is what is referred to as an anticipated queue. And so here we're just clustering the vehicles that are waiting at the intersection, and also those vehicles that are expected to join the queue before the queue can clear. So here, when the light turns green, there'll be some startup lost time as cars get moving, and the vehicle that's approaching behind will be in the queue before it even gets close. The idea, the simple idea is then to use these larger clusters as the units that we'll build this timing plan around. So with that in mind, then the scheduling problem, it really looks like one of just sequencing clusters that operate on competing phases. So here, if you think about, maybe you have two input flows. Think of an intersection where you've got two one-way streets coming together. It's the simplest kind of approach you can get. And so I've got clusters coming toward the intersection on both, in both directions. One light is green and one is the other. And the scheduling problem then is just to build a sequence that gets all those clusters through the intersection. So a schedule is a sequence of clusters. We assume, at least for now, non-preemption, so the jobs are indivisible, so you've got to switch on a boundary. And you can see that here's an example of the schedule, and actually you can see that in putting them into a single sequence there, it was necessary to delay movement on some, so everything's not moving perfectly there. And that's due to the constraints, such as it takes a certain amount of time to shift from one phase to another. There's a yellow, and in Pittsburgh there's an all red phase, which we've just collectively called yellow here. So once I have a schedule, then I can, if I get a schedule, then that implies that I have a signal sequence that I can turn into a timing plan. There's still flexibility for deciding the plan, because there are many places along those switchover points where I could actually terminate the phase, but I've got that phase. So the problem then that we solve for the intersection is just to minimize the cumulative delay of all those jobs, subject to timing constraints for safety, which correspond to the yellow and all red time, and the fairness constraints, which essentially amount to minimum and maximum times on each phase. So you give everybody a shot, a certain amount of time to shoot through, and there's a maximum. So we solved this problem doing a forward dynamic programming search. It's where we simply add a new job at each decision phase. We can take advantage of pretty powerful pruning conditions to eliminate the dominated solutions at each stage, since we have a regular objective function. So if I get to a certain depth in the tree and I'm at the same current phase, I have the same clusters on the timeline, just in a different order. I can always take the one that minimizes the delay with confidence that that'll dominate. It does dominate. We do one kind of, in cases where we are greedy in one respect, in that we will only preserve the state with the minimum delay at each extension. That just gives us speed. But what we have done, I didn't show you the classical formulation of the problem, but what we've done is turned a problem whose complexity is typically exponential in terms of a planning horizon, which kind of limits how far you can look ahead or limits the precision with which you can look ahead. We've turned that into a problem whose complexity depends on the number of phases and the number of clusters, much smaller numbers. And in fact, if you think about the horizon that we're likely to be solving for, it's very, it's a very manageable kind of computation. In fact, we have shown that experimentally that we've been able to not only produce better solutions from the standpoint of minimizing delay, but we've been able to do that in 2 to 4 orders of magnitude faster than the current state-of-the-art approaches. So it's really this formulation idea that has that gives us the leverage to go. With respect to coordination, as I mentioned before, we optimistically assume that everybody's going to follow their schedules, so that if I communicate planned outflows from one intersection to its downstream neighbor, that really just amplifies the local view and gives me a longer planning horizon. So that's basically what's happening here. Some properties of this basic protocol: it's scalable, since we only communicate with direct neighbors. In fact, that's a principle in the system. At the same time, we can incorporate indirect impact of intersections that are 2 or more hops down if our planning horizon is sufficiently long enough. So we don't give up that opportunity, but we greatly sort of simplify the scalability. We can get into trouble. One of the mechanisms that we have for miscoordination involves spillback. It's a condition where queue size can exceed the physical capacity of a road. If you're in a tight urban setting, I'm sure you've all experienced it, where you're approaching an intersection, but cars can't get through the intersection because of the backup, and that's a phenomenon that's referred to as spillback. We do some computation to decide if we see that the next phase, when we're building a timing plan, if we see that the next phase is expected to exceed its capacity, then we'll cut the current phase short, essentially giving up on our locally more optimal solution to the good of the more global perspective. So sacrifice our local interest for the sake of upstream neighbors. Another coordination protocol that we've introduced recently is what I've called here network-driven actuated control. Here's the issue, is that, if I think about it, the larger I can make the maximum times for a phase, the maximum time constraint, the greater flexibility I give to the adaptive system. And that gives me the opportunity to do more optimization of the overall traffic flows. However, the longer I make those maximum times, the more likely it is that that any kind of traffic that I have on minor cross streets is going to suffer. So that's the trade-off, or that's the dilemma that we'd like to pay attention to. Rather than just take the optimized solution that the system gives, if we can find some opportunity through coordination to do better than that, we will. So the basic idea here, what we've realized is that for intersections to communicate another piece of information around to their neighbors. Basically, we communicate phase change information. Whenever an intersection changes a phase, it communicates to its neighbors that it has changed and when it expects generally to be moving on to another phase. With that information, you can do such things. In this particular case here, upstream neighbors can interpret that information as some kind of a service time constraint. And so as long it can do it, let's say the downstream intersection is in a cross flow, okay, and the upstream intersection is green. If I've got side street traffic, and I may be green because mainly I hardly ever see side street traffic, but if I do have somebody waiting, either a vehicle or a pedestrian, and I can service that cross street and get back into the flow before the downstream intersection switches phases, then I haven't delayed any vehicles, but I've serviced that cross street. So this is sort of a newer optimization that we've just put into the thing. Okay, so let's as I said, we originally got good results in simulation, so we started looking for an opportunity and talking with the city of Pittsburgh on where we might try this out and see how it works in practice. And we settled on a 9-intersection grid in East Liberty, just a couple miles from here. I'm gonna try to get out of this for a minute and see if I can show you. See if I can find this. Essentially, I'm stealing a video that was not stealing. They allowed me to do it, but this is a video that was made as part of a concept proposal for a project to relocate the East Liberty busway, and this is just a portion of it. That, whoops. Okay, that kind of shows the area of interest, and I guess one thing to sort of note about this is that East Liberty is this area that's sort of been undergoing a lot of change in the last few years. So here's one aspect has been that they've changed from a one-way grid to partially a two-way traffic scheme. A lot of that came along with the development of a new Target store. And all right, this is maybe too much. And I guess the point is that we're actually involved in this Tiger grant, which has been funded and will allow us to do some expansion of our network. But East Liberty as a region is really undergoing a lot of economic development, and in fact, from their perspective, us coming into to this area has really been a benefit to them, in that it's sort of a selling point, a spurring of economic development. But basically, the pilot test site consists of 9 intersections. The 8 intersections in blue surround the Target department store, and as part of the Target development, which happened, I guess, about 2 years ago now, or a year and a half to 2 years ago. Those 8 intersections were all rebuilt and equipped with camera video detection. So they gave us a very relatively low-cost way of testing out the system. And in conversation with the city of Pittsburgh, the city traffic engineer suggested that maybe we add this 9th intersection at Penn and Highland, which we did, which we were able to do, thanks to the Heinz endowments. And that gives us more of a grid pattern. So if I look at this area, there are really 3 dominant flows. There's the flow on Penn Circle, which is kind of that reverse L shape. There's also a flow on Penn Avenue moving east-west from the red circle on that way. And then there's a third flow coming north on Highland from Shadyside. So actually that flow is temporarily blocked at the moment because the bridge is out. But at the time of the study, there were these 3 flows. So a nice example of an urban grid setting, a nice place to try it out. One other characteristic about this that makes it especially tough, the intersections are some places very close together. 150 feet maybe, the smallest one intersection. If you compare that to the kind of work that's typically done in adaptive signal control in the literature and so on, this is, they're usually looking at intersections that are frequently like a kilometer from each other, or on that scale. So very tightly spaced intersections. Here's a shot of the hardware configuration. So for those of you the box on the left is, if you know, lots of times you don't notice them, but at every intersection you'll see some kind of box like that. That's where all the equipment is that drives the traffic signal. What we did is actually put another CPU in the box at each intersection, along with network gear to allow us to exploit the communication infrastructure that was in place. When they replaced the lights, they actually put in fiber optic cable, which was great. It wasn't being heavily used, but we take advantage of that. And then the one intersection that we added, we added radios to allow us to communicate between that light and the rest of the light. We definitely need communication. That's a prerequisite for it. And then there are traffic-on cameras at all the intersections that provide our sensing. And so essentially the cameras, or the video, the processing boards, and the interface to our machine, we get the results in real time from the detectors, and then we issue calls, commands to the hardware controller to drive the actual intersection. Here's a diagram of kind of what you see when you look through a video camera, and sort of a typical placement of of the detectors. You know, we're using video cameras, and you have the opportunity to draw various kinds of zones that allow you to do certain kind of detection. So presence zones just detect the presence of a vehicle sitting at the intersection or moving over that space down at the bottom. We can also define, looking further back, data zones which allow us to do some counting of vehicles as they arrive. We also, in the East Liberty case, there's a lot of one-way exit lanes, or one lane traffic flows. So we also, for any internal node in the network, we can define exit counters to count how many cars are leaving the intersection. For interior nodes, that's sort of an advanced detector for the next intersection down. System operates in a sort of a non-disruptive way. When we first started, we were kind of very cautious about you know, screwing up the traffic flows in the area, and so the system is built in a way that we simply override the pre-existing plans that are built into the system, the pre-existing control strategy. And if anything ever goes wrong, the system just reverts back to what was there before. That hasn't actually happened yet, but there's some concern. We also tolerate some amount of loss of communication with our neighbors. We're a totally decentralized system, so we're getting information from, if we have a network, any kind of network problem, we'll detect that after some period of time, and then automatically shift to using sort of moving average historical data until we come back online again. So note that gives us a very sort of robust infrastructure, in the sense that while we may lose information in one direction, we are in a grid typically, so we're getting information from all directions, and so we can still operate with whatever real data we have. We've also done some amount of work in trying to reduce uncertainty by you know, integrating information from different sensor sources. You know, in retrospect, it's not surprising, but you know, going out there, we've sort of really realized the impact that sensors are not necessarily reliable. You have, you know, you'll have big trucks going down both lanes. You'll have sharp turns missing our detector zones, and so there's a lot of uncertainty in the reading. We're waiting for the day of connected vehicles so that we can have much more precise information about who's coming toward the intersection. Here's just a quick video that we took one day last August, sort of a before and after at the, this is the, whoops. This is the main intersection at Penn and Penn Circle. So we're looking at the traffic west, going west is coming towards us. And one afternoon we turned our system off for a while and ran the old one, then turned it on again and ran the new one. So you can kind of, this video is sped up like I think either 4 or 8 times to kind of give you a sense of the flows rather than the typical vehicle. And I think, you know, if you kind of watch it, you can kind of see the smoother flow on the right. Hopefully you see that. We did conduct a formal evaluation, and so let me just say a little bit about you know, how we did what our pilot evaluation looked like, how we did it. Well, we first identified the 12 highest volume routes through this grid network. So those are they're indicated by the blue links there on the left. Each direction is considered a different route. And then for each of those routes, we did multiple drive-throughs with you know, with an app, essentially using a GPS app to track our paths and you know, sort of let us detect sort of how fast we're going, you know what basically the trajectories, how many times we stopped, et cetera, et cetera. So we conducted multiple runs for each route during each of 4 periods of the day: AM rush, PM rush, midday, and evening. And we did that both for the pre-existing the way the signals were controlled prior to our introduction and running with the SURTRAC system. And then we just compared transportation efficiency and emission reductions results. The pilot test was, I guess I had it on the slide, but I failed to mention it, but it was funded by the Heinz Endowments as part of their BREATHE project, which is really concerned with air quality. And so their real interest in seeing this technology tested out was in seeing what kind of impact it could have on reducing emissions. So you know, obviously that's one of the areas that we were studying. So here's a few more details about the study. The AM/PM rush, you know, what we were comparing to was a coordinated fixed timing plan that was generated originally using an offline optimization tool called Synchro. Synchro is a state-of-the-practice kind of tool that's used by traffic engineers to try to optimize the coordination in advance based on what the expected flow patterns would be. So those offline optimized tool plans were used during the rush periods. And then in the other periods, the system just ran in actuated free mode, essentially keeping green on the main drag, whatever was defined to be the main drag. And then whenever traffic was detected at a cross flow, you know, giving time to that and then moving back to the main flow. So these plans were put in place, I think, maybe about a year prior to when we ran the experiment. So that's actually, you know, that's actually a fairly decent, fairly small, fairly recently compared to the overall scheme of things. A lot of times traffic plans are in place for years and years and years and decades because there's no money to retime them. Anyway, the after condition was our system. We did 3 runs for each of those conditions and periods that I talked about. All runs were carried on Monday, Thursday, except for we did do one 4th run on the PM rush on a Friday for both before and after, different Fridays. But because we experienced that to be really the heaviest time, at least during the period that we were doing it. We conducted the fixed or the pre-existing runs with the pre-existing system in March of 2012. We intended to do the adaptive runs immediately after that, but we ran into some sort of difficulties. It took us a couple months to work out a legal agreement to take over the lights with the city. And so we were stalled kind of while that happened, and then when that happened, we ran our adaptive runs in June. We did do a load analysis of those two periods and found that essentially they were the same. We had a 5% increase in traffic volume from March to June. So if you think about it, I guess the adaptive SURTRAC had a slightly heavier load to deal with. We got great results. Here's a kind of a summary. We have a report that describes the results in a lot of detail that's available for anyone. But what I've done here is just shown you the aggregated results, both for periods of day and overall. The aggregations are all, we use traffic volume data to combine routes as we aggregate it. So, but you can see overall we got a over 25% reduction in average travel time through the network, an increase of 34% in speed, number of stops, decrease of 31%, a reduction of 40% in wait time, so that's great. And then using a standard fuel consumption model, we computed what we projected the reduction in emissions to be of 21.5%. So super results. You know, actually, we were pleased. The system's been running now continuously since June. We've been, we've been doing a couple different things. Our current focus, we've gotten funding to expand the pilot test site eastward toward and around Bakery Square, out toward 5th, kind of moving that way eastward. And that will incorporate 9 more intersections, essentially double the size of the test site. One of the issues that we're very interested in now is demonstrating. We believe our system to be arbitrarily scalable, but we like to really demonstrate the fact that can get there. We're also working on generalizing and improving the system in various ways. The one coordination protocol that I discussed a little earlier is a start towards giving more active attention to pedestrians and bus movements. I'll say a couple more words about that in just a minute. We're also looking at the problem of flexible phase selection, and I'll say something more about that. But along with this current expansion, we also have a proposal pending to expand the pilot the other direction, and we really expect this to happen over the next year and a half. The city of Pittsburgh has funding starting this summer to upgrade the controllers and the communication infrastructure from East Liberty going back along the Baum and both the Baum and Center corridors to Craig Street in Oakland, basically. So we're proposing to piggyback on top of that. That will give us the control requirements, add detection to these intersections, and then adaptive control. So this is our slightly longer term plan, and one of the visions that we have is what I call an East End downtown corridor. This is a larger granularity map where at the bottom moving across the bottom is the Parkway East coming into town. You can see where it goes underground to the Squirrel Hill Tunnel, which I think the second most congested spot in the state, following the Schuylkill Expressway in Philadelphia. So, but if you think about the deployment that we have, sort of the expanded test site that I talked about would cover that circled area there, and you can see from Craig Street to downtown, there's 3 signals, and going in the other direction towards Wilkinsburg, PennDOT actually has a project, is going to be installing radar detection on the 6 intersections that go from where we'll end up at 5th down to Braddock Avenue, essentially near the end of the city of Pittsburgh. Wilkinsburg, so then you could see at this point you have two paths, one through Regent Square and one through Wilkinsburg that would put you, you're not that far away from having sort of a virtual, an adaptive alternative to corridor to the Parkway East. So there's, so there's good momentum, and we've talked with Wilkinsburg about this. We did a study for Hines on what it would look like if we did all the intersections in Pittsburgh. Who knows whether that'll happen, but certainly we can have a good positive impact without too much, extremely positive impact without doing too much more expansion. Let me just say a couple words about some of the work that we're doing now, and then I'll stop. I'll finish. One of the concepts that we didn't put to use in the pilot test, but is used in different kinds of signal systems, mostly conventional systems, is the idea of phase skipping. And the issue is the following, that if you have changing traffic flow patterns over the day, they can make various phases more or less essential at different times of the day. So, a prime example of that might be left turn signals that take up time, block traffic in the opposite direction, and at certain periods of the day may be heavily utilized, and other periods of the day may not be utilized at all. So you can gain great efficiency in general over the day, I think, if we can detect those kinds of situations and skip phases when there's no waiting traffic. So that's the goal. The trade-off or the challenge is that phase skipping, or more generally, if I want to just arbitrarily select phases, increases the uncertainty that's associated with the planned outflows that I communicate to my neighbors. So it's very possible that as I add more flexibility to skip phases, I can degrade coordination through the network, because I'm now less confident about what phase is coming next, and how do I coordinate. The solution that we're pursuing, we've actually been testing, is for a given intersection to identify the subset of guaranteed phases that we'll always want to execute, and then generalize the phase sequence into more like a phase transition graph, so that from any given phase I can move to any number of successive phases. Having that graph, then I can start to think about constructing and maintaining transition probabilities. So that's our idea, is just to build those probabilities from historical information, and now we can kind of track on a moving basis what phases are most likely, are being most used and underused, and use that information as a basis for deciding what kind of information to communicate to the neighbors for planning purposes. So I can decide that my most probable next phase is this, so that's what I'm going to use when I'm planning outflows this time, and then we'll adjust as they come to pass or not. So that's one idea that we'll be trying to evaluate in the short term. Another longer term problem that one of my students, Arvind, is working on is a real-time bus detection from video. Yeah, you know, the idea here, well, the idea that spurred it really is that within robotics, we've had some recent success in exemplar learning using support vector machines for general sort of object detection. And this is not a real-time computation by any means, but the idea here is that by exploiting the structure of this setting, the fact that the cameras are rigid, don't really move, you know, we can localize where we're looking and what we expect to see in the frame, that we can get this. We can utilize this in a way that will allow us to track buses in real time. So that's kind of what that's what he's working on. The benefits, we really see the benefits as passive, low-cost detection. There's no need to equip buses with sensors. If that's an easy thing to do, we're all for it. But in those circumstances where that's not feasible, you know, this gives us an alternative way of recognizing. In any event, if we can know the bus, you know, the reason we want to detect buses is so that we can do some kind of a balanced prioritization, that we can integrate it into our adaptive signal algorithms, so that if we recognize the bus is picking up passengers in his dwelling, we can service cross traffic, for example, and so on and so forth. So we've gotten some decent initial results, but we still have a ways to go on that. Finally, some other research directions. You know, what we're optimizing right now, and what we have been doing is optimizing traffic flow metrics, minimizing cumulative delay. But one can also think about optimizing for other kinds of effects. So, for example, optimization for environmental impact is one area that Heinz is certainly interested in, and we're interested in generally. You know, conventional argument says, and to some extent this is true, that if I optimize traffic efficiency, I will get the secondary benefit of minimizing or reducing emissions. But it is possible that you would get a different trade-off if you emphasize more those metrics that correspond or relate more directly to environmental impact. So, for example, I might think about minimizing number of stops rather than you know, optimizing speed, or you know, so this is an area that we've begun to think about. You know, we believe that you know, as long as the objective function can satisfy certain characteristics, we should be able our search procedure should translate. If it doesn't, I'm sure we can find a search procedure that can do it. Another strong area of focus for us right now is what I'm calling multimodal traffic management, and you know, particularly in urban environments, which is our main focus. We're really interested more generally in integrated optimization of all modes of traffic: vehicles, pedestrians, bikes, transit flows. So, you know, we've started to take some steps in that direction towards giving attention to, greater attention to pedestrians, for example. And we are intending to, through that Tiger grant that I was mentioning earlier, we are intending to acquire some pedestrian cameras that would allow us to perhaps do things like detect volumes of passenger traffic and along passenger pathways, sort of, in a sense, integrate those flows into the overall adaptive algorithm. The final area that we've started looking at is the broader issue or broader concept of monitoring and shaping traffic flows. We're doing some experimentation right now with showing the impact of using routing information and a route generator iteratively to adjust traffic flows, so that you know, as I get a certain amount of volumes moving in certain along certain paths, naturally I'd like to start to exploit those routes that are under capacity. So if I look ahead, or if we look ahead to you know, the time when vehicles start talking to the infrastructure, you know, now it becomes very possible to think about using the information that I'm collecting as I'm managing traffic flows together with information from vehicles, if they're willing to share where they're going. I can use that to kind of shape flows and you know, perhaps you know, solve this larger optimization problem. So that's one of our broader visions. And we're going there. So let me just finish by sort of reiterating, I'm not sure I really ever said this, what we see as the key advantages of the approach that we're pursuing right now. First of all, we're offering true real-time response to traffic conditions. We can compute near optimal phase schedules. We can compute them as frequently as once a second. We have plenty of headroom in that once a second, so you know, one can think about introducing more sophisticated coordination between intersections without affecting that ability. We manage multiple dominant flows as opposed to just single corridors, so there's no need for any kind of global information about a designated dominant route. We believe our approach is scalable to road networks of arbitrary size. It's also has the advantage, as you kind of see with our expansion, that we can grow it incrementally. All you need to do is be able to connect the new intersection to the existing network and put a computer in the box. Well, assuming you have detection, but that's quite different than you know, sort of a system that requires sort of an overall sort of central framework to build. So it gives a kind of a low-cost way of proceeding. And then we really are designed, I didn't talk much about it, but our software architecture is aimed at promoting use with whatever equipment is out there. So, you know, in one sense, you can think of this approach as using the auto industry as a kind of an aftermarket kind of approach. We would like to be able to use whatever hardware controllers are out there, assuming they have the minimum requirements, and whatever kind of detection is out there. We're using cameras now, but it looks like for bomb center, we may, in fact, move to radars, and you know, there are other kinds of detection as well. So, okay, so I think I'll stop. Thanks. Wore you out, huh? Yeah.
I have two questions. Does the system consider emergency scenarios, like, for example, detection of an ambulance if there's a lot of traffic?
No, we're not doing that now. You know, we certainly could interact with emergency prioritization system. You know, typically emergency prioritization right now is, you know, you just get greens as far as you can see if you're the emergency vehicle, and you go. We're not integrated with that now. I mean, it's something that could easily be done. Yeah.
And second, can the system be applied in, for example, developing countries where I see mainly two challenges. One would be like vandalism with cameras and equipment, and the other one would be people don't tend to respect the rules as they do here, like they will change the lanes constantly. So perhaps that affects the system.
Well, the second one, interestingly, people don't respect them too well in East Liberty also, this changing lanes. We've currently not made too much use of lane-specific information. We thought we would initially, but you know, we found that was very unpredictable, and unless there are specific lane, like turning bays, you know, we tend to just look at the traffic that's coming towards us in all lanes at once. So that problem, I think, I mean, I don't really see that as a big problem. The other, the money issue, is that?
Vandalism, because like perhaps if you put cameras or equipment on the street, it might either get damaged or stolen.
Oh, all right. Oh, yeah. Well, yeah, I don't know. I don't know. Do you think the U.S. is any less vandalist than other countries? I'm not sure about that. I don't know. That's definitely an issue. Yes. How good was it? Yeah. I mean, it's no, maybe Shelfang, you could say something more, but there are periods when it's very bad, and there are you know, periods when it's good, I guess. You know, and, one of the motivations for the city wanting to prefer radar is that they're more accurate in inclement weather, I guess. Well, yeah, yeah. You know, I hear what you're saying. Yeah, and we haven't really measured that. I mean, I know on occasion, on a bright horizon, you know, looking down one direction, you may be blinded for 5 minutes, or you know, a wet. What we do is we do a lot of kind of cross-referencing of different of sense counts, you know, at different road segments. So, you know, so we're constantly looking at seeing whether what we expected to be coming in is matching what we're seeing going out, and doing some adjustment on that basis. But between different instances of information that's been passed to us. Yes.
Your information comes from signals and information at the intersections and lights. One of the problems on Center Avenue is that giant Eagle store, with lots of people turning in and turning out and turning directions. So it would be interesting to see how that works without that. But also to put a light there so that allows you to maintain control as to what the major bottlenecks on that route.
Yeah, that's interesting. I mean, we have some much more minor versions of that in the current test site, but you're right. That, you know, another intermediate option might be to have some kind of a detector there without a full-blown light. But you know, if we could put a detector just to detect the outgoing, you know, the things coming out or the waiting there. Yeah, yeah. Yeah, yeah, but that's an interesting point. Baum Center has a lot of interesting challenges, I think. Yeah, yeah. Yes?
What is the metric according to which individual candidate patterns are judged? Is it the number of vehicles stopped at a particular intersection, or the number of vehicles dispatched?
If we're comparing different plans, is that?
Exactly, when the computer compares different plans.
Yeah, yeah, yeah.
Okay.
Right now, we're evaluating we look at the plan and we decide what's going to be the cumulative delay on that plan. So how many vehicle clusters are going to have to wait and how long, if that plan executes exactly as planned. And then we take the minimum one of that.
The delay until all vehicles have exited the intersection. I see.
Yes. Within our planning horizon. Yeah. Yeah. Yes. We make an assumption of what the speed is going to be along each road segment, basically.
So from your camera, you're just counting the vehicle that's passing right now.
Right, right. And we can update that. I mean, our goal is to update all these parameters as we collect information so that we keep current with them. Yeah. Yes. Well, I think the primary advantage is that they're more accurate.
Is cost anything?
Cost is about the same, maybe a little bit more, maybe a little, but not too much more. I don't know. How would Greg? How would they compare to infrared or something like that? Yeah. Yeah, so they don't cost that much different. Okay. Okay, great. Thank you. Yeah.